This is the do file that I posted in the Blackboard folder for the week. So we always save the data to courses slash HEA 46901, so on. There's a website that sits out there at the university website that's linked through Blackboard, and that's where I store all the data sets. So this week it's called birthweight.dta. So .dta, that's the extension for a stated data set. So when stated data sets are nice in that they're the same on Mac and Windows, and that you can move them back and forth between things. So when you're working with people in groups, I've done some sort of what they call team science before, and you're sharing code, you're sharing data, that you could use a Mac, Windows, Unix as well, and Linux, whatever you have, you could use data on it basically. So the data set's birthweight.dta, and then what we're going to do is we're going to analyze two variables, LBW and smoking. So LBW, that stands for low birth weight. So LBW is equal to 1 if it's a low birth weight baby, and LBW is equal to 0 if it's not a low birth weight baby. So LBW 1 low birth weight and LBW 0 normal weight. And then similarly, smoking is equal to 0 or 1. So 0 if the mother did not smoke during pregnancy, and then 1 if they did smoke. So make tables of it, and then row is going to calculate what's called the row percentages, because then you can see of the low birth weight babies, which percent had a mother who was smoking during pregnancy, and then which percent did not. Chi-square, that's the chi-squared test, so the Greek letter chi-squared. So that's going to calculate a p-value of just a basic, simple relationship between low birth weight and smoking, or to roughly estimate a relationship. And then exact, that's going to calculate the chi-square test exactly, a little more detailed calculation, but you'll see that the result's the same. And it'll also add the one-sided test. So normally, a chi-square test is just looking for differences, right? So are low birth weight and smoking related? Is the rate of low birth weight different between babies whose mothers smoked during pregnancy and babies whose mothers did not smoke during pregnancy? Now, a one-sided test is you have a bit more of a specific hypothesis. So two-sided tests, are they different? Is it higher or lower? Then one-sided test would be, okay, if we're going into the study and we think we already have evidence that smoking sort of is a risk for low birth weight, and we thought that low birth weight would be higher among babies whose mother smoked during pregnancy, well, then we would have a one-sided test where instead of just seeing whether or not it's different, we're seeing if it's higher. And in other types of studies, you might think it's lower, right? So two-sided tests just are they different, and then one-sided test, your hypothesis is either that it's higher or that it's lower. Two-sided test is that it's either higher or lower, sort of either is fine. You're just testing for a difference. They'll all be the same here. So all the p-values are going to be really low, and really low p-values, really tiny p-values, those are highly statistically significant. It's the chance that you would get the result by accident, right? So you get some result of the study, and then if the p-value is like 0.99, well, then it's not statistically significant. There's a 99% chance that you just get that result by chance. Versus if the p-value is like 0.01, well, then yes, it is statistically significant because there's only a 1% chance you'd get the result by chance. You'd get the result by accident. And so p-values are between 0 and 1. If they're really low, it's statistically significant. Generally, the cutoff's 5%, so if a p-value is less than 0.05, then it is statistically significant. So 0.01, yes, statistically significant, 0.02, 0.03, 0.04, and so on. Those are all statistically significant results. Versus if it's greater than 0.05, so we're talking about a p-value of 0.06, not statistically significant, 0.07, 0.08, 0.09, not statistically significant. So I always replicate the data from the book. I match the data, make the data match whatever's in the book. It's sort of a weird thing to do because you're normally not doing that. I mean, there are times where you'd sort of generate data, right? If you're creating like a random variable, or you're randomly assigning things, or you're doing certain types of simulations. But generally, you're just going to be analyzing data that's existing or downloading data that's exists, or sort of like I do a lot of combining data sets. So sort of the process of how I create data here, you can see that I'm showing you here. And again, if it's in green, right, these are just sort of comments, so it's not the part of the code, but I left it here so you could see it. So I'm creating the data to match the book. And CC is what's called a case control study. So case control studies, it's language that comes from epidemiology. So when we did the experiment, when we did last week, when we did PUFA vitamin, PUFA plus vitamin placebo, that's sort of more of a cohort study where you have these groups of people on these different treatments and you follow them forward. Case control is the opposite, where you take low birth weight babies, not low birth weight babies, sort of trace their medical history and you see whether or not the mother smoked. And then you can see, okay, of the low birth weight babies, what percent had parents who smoked? 33. And then of the not low birth weight babies, what percent had parents who smoked? 20. And then is the 20 different than 33? And what's the odds ratio? What's the likelihood of sort of smoking in relation to low birth weight? The likelihood of low birth weight in relation to smoking, say it either way, it's 2, right? So it's twice as much. So the risk of low birth weight is twice as much if the mother smokes. At the risk, the odds are twice as much. It's twice as likely. Risk is something else. Risk and probability, I actually think, is an easier language, but epidemiologists love odds ratios, right? The odds of low birth weight are sort of twice as high. And social scientists, we say odds ratios are odd. Well, they're odd. They're sort of hard to think about because it's not actually twice as much. Um, when you take epidemiology or research methods, or when you took those courses, they might have done odds ratios. So we'll see an odds ratio of 2, but then we'll just graph it in terms of the risk, and we can see that we'll just graph the probability of low birth weight by smoking and not smoking mothers, and then we'll see that it's higher among mothers who smoked. So when you type CC, that's the case control study, and that'll sort of give you like a more formal p-value than when we just did the tabulations. So let's just press edit, select all, press do. The graph will pop open. Remember, highlight everything, press play. It should do that. And I've always been posting the recordings as well, so the recordings are always posted right after class. So you could access those, and email me if you have difficulty accessing the recording. So that was where I was making the data there. Let's go back and look at what we have here. So, okay, so we open the data, and then, okay, so you see that there were a total of 950 people in the study. 400 were the mother did not smoke and they were normal birth weight. 300, the mother did not smoke and they were low birth weight. 100, the mother smoked and they were normal birth rate. And 150, the mother smoked and they were low birth weight. And then what this does here is when you type row, it's going to add what's called a row percent. So they add up to 100 across the rows, moving across the tables. So when you add the row percent, you could see that, okay, of normal birth weight babies, 20% of the mothers smoked. Of low birth weight babies, 33% of the mothers smoked. Right, so normal birth weight and the mother smoked, there's 100 of those babies. And then you see 20.00, 20%. Low birth weight babies and the mother smoked, that's 150 of those. And you see 33.33, 33% of the mothers of low birth weight babies smoked. See the chi-square test here underneath the table, it's going to add PR equals 0.000. Again, it's not actually 0, it's really tiny, it's less than 0.001, and that's less than 0.05, right? Really small p-value, negligible p-value, statistically significant. So yes, the study results are statistically significant. Chi-square exact, okay, so just calculate it using one method, Pearson, calculate it using a little more detailed method, Fisher. And if we had a biostatistician, they could explain to us what the difference is if we wanted to know a little more about the math. One-sided, okay, now just have a hypothesis that goes in one direction. We think that smoking increased the risk of low birth weight rather than just thinking it was somehow related. So no matter those 3 different ways of calculating the p-value, they're all statistically significant. And now this is a little more formal analysis where we do CC, that's the case control study. So exposed, unexposed, that's smoking, non-smoking. Exposed, mother smoked. Unexposed, mother did not smoke. So the exposure is whether or not the mother smoked during pregnancy. Cases are cases of low birth weight. Controls are normal birth weight. So the idea here is you're taking normal and low birth weight babies and you're looking back throughout their history to see whether or not the mother smoked. You're doing like a survey of the mothers or so on, or better, you're testing the mother's bloodstream for whatever whatever the biomarker is of having nicotine in the bloodstream. So again, it matches the table above it where, okay, 150, those are cases, so they're low birth weight and they're exposed, so the mother smoked. 300 cases, low birth weight, unexposed, mother did not smoke. 100 controls, normal birth weight, exposed, mother smoked. 400 control, normal birth weight, unexposed, mother did not smoke. Odds ratios too. So it's what's the relationship? Well, it's twice as likely. The odds of low birth weight are twice as much if the mother smokes. Between 1.5 times as much and 2.7 times as much. That 95% confidence interval is a range around that odds ratio point estimate. Proportion exposed, go back to the top right of the table, so 0.3333. Remember we said 33% of the cases of the low birth weight babies had mothers who smoked, but only 20%, 0.2000, 20% of the controls, the normal birth weight babies, had mothers who smoked. Proportion exposed. Proportion of low birth weight exposed to the mother smoking during pregnancy. Proportion control, proportion normal birth weight exposed to mother smoking during pregnancy. Look at the bottom of the table, 0.0000. That's statistically significant, probability greater than chi-square. That's similar to the chi-square test we ran above. PR greater than chi-squared, that's the p-value, 0.0000. Again, it's a probability, so it can't be 0 and it can't be 1. It has to be between 0 and 1. So it's not really 0.0000, even though Stata says that. We'll say it's less than 0.0001. And then when you do a graph of low birth weight, it'll look like this and see that, okay, so among mothers who smoked, about 60% of the babies, 60%, were low birth weight. And then if the mothers did not smoke, about maybe just over 40%, right, just over 0.4, just over 40% of babies were low birth weight if the mothers did not smoke.